visible, ma'am?
Yes, ma'am, it's visible. You can make it into full slideshow, ma'am.
This is actually a PDF.
Okay, okay.
This is how it will actually show. If you want, I can increase, but then one whole thing will not come in.
Okay,
Maybe
ma'am.
this is better. Yeah.
Yes, ma'am. Yes, ma'am. Ma'am, you have to increase your voice, it seems like, from the feedback.
I have to increase my volume.
Volume. Yes, ma'am.
Okay. Now, is it better now?
Yes, ma'am. Yes, ma'am.
Otherwise, I can use, actually my computer volume is a little bit low, I'll be honest. I can use
Okay.
a mic, but
No.
that will also add some artifacts, little bit, some krr sound might come.
No, ma'am. Now it's clear, ma'am. They have missing.
I said, uh, this will be a lot clearer, my voice will be clearer, but some echo kind of thing will be there, slight echoing. Is this better or shall I just go back to my normal voice?
Yes, ma'am. This is also better, like, but previous one is okay. Like, it's clear.
Previous one was okay. Okay, fine.
Yes.
We'll go back to that. Yeah.
Shall we start, ma'am?
Yes, ma'am.
Oh. Good morning, all. To one and all present here, I, Dr. Patil Monica, Assistant Professor, Tripoli Department, Bardhaman College of Engineering. I heartily welcome you all for the FDP on Applications of Power Electronic Converters to Power and Energy Systems, Day 2. The importance of this FDP is to analyze and evaluate the numerous emerging technologies in power electronic converters and inventions, explore the impact of emerging developments in the power electronic converters. Among them, the supercapacitors are becoming the major role as fast charging discharging ability of the supercapacitors have made it more attractive towards many industries now in EVs. So we are going to discuss this topic in detail, and we have today's resource person, Dr. Anusuya Bhattacharyya Garu. Dr. Anusuya Bhattacharyya Garu received BE degree in Electrical and Electronics Engineering from Anna University, Masters by Research degree in Electrical Energy from IISc Bangalore. She has also pursued her PhD degree from IISc Bangalore. Then she was awarded Science and Energy Research Board of India postdoctoral research fellow and carried out research at the University of Alabama in Huntsville 2018. She is currently working as an associate professor with the Department of Electrical Engineering, Vellore Institute of Technology, Vellore. Dr. Anusuya Bhattacharyya Garu research interests include material testing, high voltage plasma, and nanotechnology. She has published 8 journals that includes IEEE and IET journals, 7 international and national conferences. Thank you, ma'am, for your valuable time. Now you can start your presentation.
Thank you. Uh, yeah, so as ma'am said, that I have actually done my master's and PhD from IISc, and the catch is that IISc mainly focuses on fundamental research rather than applied research. So I know this is a conference or FDP, sorry, on applications of power electronic converters, and you've got your EVs and how supercapacitors are applied to EVs. But my presentation is going to be a little bit different because it talks more about the fundamental research which is going on in EV, the kind of electrodes we are choosing, the kind of electrolytes we are choosing, why are we choosing them, and also when we look at the future of supercapacitors, the applications are not just restricted to power electronic converters, but also to there are a lot of very small energy harvesting techniques that are going to be our focus. We are already trying to harvest energy from renewables, but even smaller micro storage and processing, where actually the supercapacitor has a very big role to play, because supercapacitor energy storage is not as high as batteries, but it is, as ma'am pointed out very clearly, that its charge discharge is excellent. You can charge a huge supercapacitor in pretty much 2-3 minutes. So that's why I just wanted to apologize, because the focus will be very much towards the material science of it, and hopefully this will still be fairly interesting, and I'm sure it will be probably a little bit more novel than maybe that than other lectures that you have here. So with that introduction, I'll start. Is my screen visible?
Yes, ma'am, it's visible.
One minute. Okay. So let's obviously start with motivation behind usage of supercapacitors. And before going to the motivation behind the usage of supercapacitors, we got to see where the world is now in terms of its energy consumption. And if you actually look at the total world energy consumption projected to 2035, which is now it's 2022, maybe just one decade later, the energy demand from fossil fuels is expected to approach 1.83 BTOE, and BTOE stands for billion tons of oil equivalent in 2035. Now, there's a lot of conversation which goes on that, we will be able to find extra resources. We are drilling all over the place, and there's a lot of, and we'll be able to find coal, or we'll be able to create, or whatever. But just to note this, that already, because of this, fossil fuel is more concentrated in certain regions of the world, and unfortunately, India is extremely, gifted with enormous amount of natural resources. We cannot say that we are doing badly on that, but we are not gifted with oil and coal to that degree, and that creates a economic differential which all of us have to suffer, our taxes and all the money that goes to the government. A large amount of it is being utilized to import oil, gas, maybe even coal sometimes into our economy. And if you look at, I mean, I've been to Abu Dhabi. If any of you have been to these oil-rich Middle Eastern countries, the people, the original owners, they do not work. They just employ other people and they are still extremely rich because of the resources that they have. And this is a very, very precious resource. It is being utilized by us every moment. And because of that, there's a tremendous economic and economic differential that happens in the world already. So the way India can combat this, and the way India has already started to combat this, is of course utilizing its renewable energy resources. And as I said, as far as renewable energy is concerned, India is gifted. We are at that band of latitude and longitude where solar is an excellent option for us. We can build a lot of solar plants, and obviously we've got enormous amount of coastal regions. So is this pointer visible, ma'am? I'm moving a pointer.
Yes,
Is that
yes, ma'am,
visible?
it's visible.
Yeah.
Yes, ma'am.
So we have an enormous coastline. We have tremendous rivers. I think a lot of us are coming together now to do river rejuvenation projects. Uh, bringing back certain other rivers which had dried out as well. So all the hydel power is again, we have hydel power or tidal power. Those are also, a big draw for us. And then, of course, since India is a tropical country, we could grow a lot of biofuels. For example, it is not only Jatropha which can give us good biofuel or biodiesel. We also have, say, this is very specific to the south, a seed called Pongamia pinnata. The oil we do not consume, but we can convert that, and in fact, I've worked with that as a biofuel. So we have these enormous range of options, but as you know very well, and this must be a topic of discussion of the reason for power converters is that renewable energy is sporadic. Except for something like nuclear and something like coal, the other renewables do not produce a continuous distribution of energy. And because of that, we need to go through power electronic converters for one. And the other thing is the energy storage becomes a major issue. So biofuels can be used as is. Biofuels, you can simply buy it and you can put it in in your car and you can drive it. But otherwise, all the other energy, renewable energy sources that we are discussing, be it solar, be it wind, be it hydel or tidal, or any of the other ones, you would see that a very good and robust energy storage method is extremely necessary. So, so this is the way to go, and this is not only the way to go for India. Actually, this is probably one of the energy storage is probably one of the biggest challenges. And if you see right from the start of this century, I mean 2000, if you actually look at the data, this is a statistical survey on the research activities which has been carried out towards supercapacitors. And this particularly presents the number of publications, including article, books, open literature, just in Google Scholar, okay, not in all the search engines, but specifically in Google Scholar. You can see there's an astronomical growth. In 2000, there was pretty much maybe less than 100 publications on supercapacitors, and now it has in 2018 it has grown up to more than 20,000. So, and this is very interesting because I mean, we can understand the reason, the rationale. The rationale is that energy storage becomes more and more important as we start our shift towards, uh, renewable sources. And as I think, I'm assuming that most of the people who are here are faculties. Am I right, ma'am?
Yes, yes.
Yeah. Okay. So,
And
you know, if,
MTechs.
huh?
MTech.
Yes, ma'am.
MTech students and faculty, ma'am.
MTech students also. Okay. So this is
2 to 3
specific.
MTech students, ma'am.
This is specifically for faculties, that if you actually are going to write to the government for funding, you will find that when you're working on anything related to renewables, and if you're working on anything related to supercapacitor, energy storage, batteries, that's really well funded. And this is something I experienced when I had gone to the US in 2018, that same year, last year, on the uh, you know graph. What the survey that I did with the Department of Energy in US as well, because we needed funding and we were writing different proposals, was that if you look at the completed technologies, for example, uh, say, generator, motors, analysis, insulation, the overall structure and frame of the power systems, those kind of projects were funded only very sporadically. Maybe you will look at all the DOJ fundings in a year and you will probably find 2 to 3 or even 5 projects on that. Uh, I would say maybe in each topic, okay, not all the topics put together. So that maybe effectively that comes to around 20-25 projects. But if you actually apply for something like a supercapacitance or battery related project, then your chances of success grow astronomically. There's like just a particular arena, say purely supercapacitors, purely supercapacitor materials, particular type of supercapacitor materials, there will be 20-30 projects funded. So in that sense, this trend is, is reflecting in the funding also because of the absolutely essential nature of um, storage issues, because all the other electronics, we've been able to achieve some good results, but battery storage is still a huge problem. I'm sure you agree. If you've got an old phone, you can completely relate to that. Now we'll go on to the next slide. uh, So for those of us who are not hip, most of us are very comfortable. We teach our students what capacitors are, and we teach our students what batteries are in their first year, first semester. But we don't usually. I'm not aware that whether supercapacitors are taught in any form or shape in the undergraduate syllabus. So some of us may be wondering what is the difference, what is so super about it. So I'll just give a brief intro about that. Uh, See, it's a pulse current system used to meet high current and specific power requirements for durations of less than 1 minute. But what basically it means is, capacitors can very quickly charge and discharge, and supercapacitors inherit that quality from the capacitors. It is similar to that of capacitors. But the other issue is, I don't know whether I've mentioned this in a further slide. No, okay. But the issue with capacitance is that, if you suppose you take a parallel plate capacitor, just the area of the plate will, because C is equal to epsilon A by D. This is a common equation almost all of us knows. So the area of the plates very much determine the amount of charge which can be stored. And I'm sure all of you teach this to students when you're talking about capacitance. Capacitance, even though it is scaled by voltage and charge, it is more like a capacity. It's like, uh, if you have a kind of a vessel and you pour some water in it, the water and the height, that ratio would be voltage and charge. And that water, you pour more water in it, the height will increase, but the capacity of the vessel is going to remain the same. Yeah, so in the same way, the area, actually the geometry of a capacitor very clearly determines the amount of charge that that capacitor can hold. So the simple concept of supercapacitor is, how can I increase that area? And we can increase that area in through many ways. So you can make the electrode or the materials which are creating the, the top and the bottom plates of the capacitor to have micropores, and we'll talk about that later. Mesopores, micropores, and all that, porosity, increase the porosity such that there is more area for the charges to go and sit. That immediately increases the capacitance, and the capacitance, as you know, is correlated with the amount of energy stored. It's half CV square. So in that sense, you can use the supercapacitor to store a lot more energy than the normal capacitor. Obviously, it's not going to be only this. It's not going to be that simple. Also, the dielectric material which is used within the capacitance, that also changes in supercapacitors, and the distance. There are other complexities, but if you want to explain it to probably one of your undergraduate students, this would probably suffice to give an idea of how supercapacitors differ from capacitances. Similarly, um, SCs, as we are talking about hybrid vehicles, cranes, trains, elevators, and all of these things which apply or utilize power electronic devices, SCs can be used to power that. But as I said, SCs are still very big and bulky, and they are also very expensive. So usually what is done is, a hybrid form of supercapacitors. I'm going to use supercapacitor and SC as interchangeably in this talk. I hope that's all right. So yeah, so you can use a combination of batteries and SCs in these vehicles and stuff. Okay. So for example, a specific example, since this is a power electronics, most of us are here because you're interested in power electronics. In drive system, diverse types of SCs are already being used to fulfill the power demand for starting and recovering the braking energy. Okay, so because at the start, you need a surge of power in some of the motors, right? Surge of current. So that surge of current, sometimes battery is not able to give. At that point, we use a supercapacitor to create that high current. And then we switch back to the battery. And similarly, while recovering the braking energy also, it seems that, supercapacitors can be helpful. You can charge the supercapacitor very fast. So when you're going on the slope, that only maybe for a couple of minutes, right? And then you're probably going on an upslope. So in those couple of minutes, I can first charge the supercapacitor, and then from there I can slowly I can charge, I can store all that energy, and then I can charge the battery. So that's the idea of, using supercapacitors in power electronic devices. So now I just wanted to show you the energy density variation. If you actually look at the at this graph, is the graph visible, ma'am? My anybody can just maybe unmute and let me know. Is the graph visible? The energy and this thing graph?
Yes, yes, ma'am.
Okay, yeah. I was just checking because sometimes tends to. Yeah, so you can see the electrostatic capacitors is this red color line. I hope it's also red in your computer. Sometimes computers change the colors. So this electrostatic capacitor, you will see it is only the energy store density is between 10 power minus 2 to 10 power minus 1. And if you look at lithium ion batteries, it is from 10 to 100, even 150 to 50 watt hour per kg is possible with lithium ion batteries. And this electrochemical capacitors is, which is my supercapacitors, are between this 10 power minus 1 to 10 power 1. So they are still now an order of magnitude lower than batteries. So that's why they're not being replaced by batteries so easily. But we are doing a lot of research work. So possibly in the future, we'll have, maybe it is very much possible if the cost comes down especially. And we'll talk about that at the end of this lecture, how to bring down the cost of supercapacitors. Um, there's a chance that, we will start using electrochemical capacitors instead of batteries. So the distinctions between batteries are in these four things: the storage mechanism, how the energy is stored, batteries and supercapacitors, the power limitations. So actually, even though the batteries store a lot more energy, it charges and discharges slow. So the power that it can give you at a particular moment in time is a little low. Whereas that's where electrochemical, supercapacitors shine, because they can immediately give you as much power as you want. So there is a power limitation there, the energy storage, the charging rate, and the charge life limitations. Now this charge life limitations, this is, we keep talking about battery life. I'm sure, you look at your laptop and everything else, say even an Apple laptop and everything else is perfectly working fine, beautiful at maybe 5 years down the line, but your battery is starting to kind of give up. So uh, batteries have something like mm, uh, the charge, the life cycle of batteries. I'll go to the next slide, maybe that will be clearer. Yeah, so the life cycle of batteries, cycle life of battery is about 1,000. And if you cycle life of a capacitor, if you see, it's almost infinite. That means cycle life, by cycle life, I mean that if you charge and discharge it, how long will it be able to charge and discharge at the same speed or capacity, and will the amount of charge that it can store start going down. So here, if you look at supercapacitor, this is pretty good. It's greater than 500,000, which is 500,000. So the cycle life is really, really good. And the Coulombic efficiency, so efficiency of charge and discharge, if you actually look at it again, this is for capacitor, it's almost 100%. Supercapacitor is almost up to 99%. And battery, it's only 70 to 85%. So there's again a phenomenal difference in the efficiency of uh, capacitors, supercapacitors, and battery. So the only thing that the battery wins on in all these parameters is, its storage capacity. But as you can see here today, and this paper was published in 2020, so there could be some changes in these values. But in 2020, this if you actually look at the amount of specific energy that a supercapacitor can store, I would say it definitely batteries are better, but it's not that big a difference, right? And if you look at all the other things, cycle life, charge discharge time, efficiency, all of them, supercapacitors do really, really well. So and the charge storage determinants, if you actually look at it, uh, capacitors, how are charge stored? So in capacitors, you have electrode area. That electrode area is where charges go and sit, and that's it. And supercapacitors, there is the electrode is, you can say, riddled with holes, and those holes are micro, meso, and even nanopores are there in those. And then there is, instead of the dielectric, we do have something which is similar to the batteries. There's an electrolyte. And in battery, of course, battery, everybody knows thermodynamics and active mass. So I will not really go in too much depth into batteries in this particular talk. Yeah. So the reason, now the question that will arise is, if you actually look at this 500,000 cycles, because batteries only require reversible chemical reactions. You know, you put in some H2SO4 and then the ions, they go, and then that chemical reaction has to be reversed, right? It can get depleted. So in that sense, SCs do not follow that method. It is the principle of SCs, and we'll go into that, is very much similar to that of capacitors. So because of that, this movement of the electrolyte and cycles, that doesn't really determine the supercapacitor energy storage. So that's why it is able to sustain up to 500,000 cycle. And the last benefit which I found from another paper is supercapacitors can operate at a temperature between -40 to 100 degrees Celsius, whereas batteries can be operated only between -20 and 60 degrees Celsius. So your car has batteries, and during the cold season it takes a while to start and all that. I mean, I suppose if everybody is from Hyderabad here or south, they probably will never have experienced that difficulty. But if some people are from the north or Kashmir or that sort of region or abroad, then clearly the temperature matters. So anyways, getting into now the types of supercapacitor. This is some of you might, if you're already familiar with supercapacitors, you're already familiar with all of this. So I apologize for that, but I'm hoping that there is a good percentage of our research, the master students and other people who are not aware of the different types of supercapacitors. So if you will allow me, I'll go a little bit in depth into what are these three types. Yeah. So the types, as is shown here, there's an electrochemical double layer type. It's called EDLC, which use the pure electric charge that accumulates at the electrode surface. So that thing that I was telling you, riddle holes into your electrodes and make sure the charges go and sit there as well. And that's the method that EDLC, this is the traditional method of creating supercapacitors. The number two is pseudocapacitance, which develops from quick and reversible surface redox processes. So not only do the charges simply going and sitting at the surface, certain redox reactions. And redox reactions mean reductive reactions or oxidative reactions. So those reactions are happening also on that surface between electrolyte and the electrode. So that actually helps us really increase the energy storage capacity. We'll talk about that. And then hybrid capacitors, which take advantage of both mechanisms. So it combines EDLC and PC in different measures, and we'll talk about the hybrid capacitors a little bit as well. So here I'm going to again, with your permission, electrochemical double layer capacitor. It's a very long sentence to say, so I'll just use EDLC, and for pseudocapacitance I will use PC. So the principles of EDLC is as follows. You've got, as I told already, you've got inadequate charge storage space in the charge storage space in the capacitors. And because of the geometry, you have very little place for the charges to go and sit. Charges are what? Charges are electrons or ions, right? So electrons are really small, but ions are pretty big. So the smaller geometry will restrict the amount of ions which actually go and sit at the surface of the surface. surface of the EDLC. And the second thing is, instead of having a dielectric where there's only bound charges, we instead use stuff like potassium hydroxide, sulfuric acid, Na2CO3 between the electrodes instead of dielectric medium. So these acids, they obvious acids or bases, they have uh, you know they are solutions, and those solutions have moving ions, and that's what actually creates uh, supercapacitance. So there are three different models of supercapacitance. Again, this is very basic. This is kind of known to many of you. I'm assuming if you have been working in the area of supercapacitors, there's a Helmholtz model, Goy-Chapman model, and Stern model. So the Helmholtz model was formulated in the 19th century, and it proposed that you have an electrical double layer at the electrode electrolytic interface. So this is the electrode, positively charged electrode surface, and that there's a obviously positive, it's charged positively, and then you've got these negative ions. So this plus and minus is forming what is known as a double layer, and they are separated just by the size of those ions. So they are basically, since ions and atoms, we know atom sizes are in Armstrong. So this double layer is thickness is the size of Armstrongs. So it's parted by atomic distance. Now we will get into why this causes supercapacitance. But what the Goy and Chapman came and said was, no, it's not simply a straight line of negative charges. There are certain solvative ions also which come into the picture, and it's more diffuse. As it is seen here, they are not sitting right on top of the positively charged surface, but it's kind of diffuse, and you've got solvated ions. Now, what does solvated ions mean? Solvated means you mix salt in water and it completely dissolves, right? You put your hand in the water and you're not going to feel some kind of a crystalline structure anymore. So that is solvation, dissolving. So what happens is you've got the ions, and around them you've got these the say for example this was water. So electrolytes are not usually water, but suppose they were, then these white circles around that positive, those will be the water ions connected to the salt. So that what happens is that these solvated ions obviously then become a little bigger. That has a consequence, and we'll talk about that a little later. But just to explain explain that this phenomena was taken into account by Goy-Chapman. And so as a result of that, so if you look at the the phi, the potential or whatever, that is lower here and it's a little bit longer over here. And then Stern came along and he combined both the models. He said absolutely close to the charge, there will be somewhat of a Helmholtz double layer, and then as we go further away from the charge, you will also have a Goy and Chapman model like layer. So it's a combined layer and both have to be taken into account. So this Goy-Chapman layer will also be referred to as a diffusive layer, because that layer has a little bit diffusion of the opposite kind of ions as well. Yeah. So so in the Stern model, the Helmholtz layer is called the compact layer, inner region, and then there is a diffusive layer. So now we'll go on to the mechanism. So as you can see, the capacitance equation is same as our normal capacitance equation, even though you're using an electrolyte and very strange kind of electrodes. So C is equal to epsilon R, epsilon naught into A by D. But here, epsilon R represents the dielectric constant of the electrolyte, or the relative permittivity of the electrolyte. And the vacuum permittivity is obviously epsilon naught. So I'm sure this I don't have to explain to electrical engineers. If you look at the representation of the electrode specific surface area available to the ionic species of the electrolyte, if you actually zoom in and look at this, the surface area, it's not plain. There are these holes in it. And these could be at the size of microstructures. It could be bigger than microstructures, maybe 100 times. Those are called mesopores. And then it could be also as thin as nanostructures. Yes? Yes, sir?
Sir, please unmute your mic.
Sure, madam.
Gunde Bhavana, sir, you have something to say?
Nothing, ma'am. Sir has joined just now.
Okay. Sorry. Is it like audibility and all, everything is okay, ma'am?
Okay, ma'am.
Yeah. Yeah, we'll go back to this. So if you actually look at these pores, you've got the blue and the red are the positive ions and negative ions, and both go and sit within the pores, increasing the charge distribution, increasing the amount of charge that can be stored. And if you actually look at some of the materials which are used, which we will again talk about, like carbon, activated carbon especially, or carbon nanotubes, or different variations and forms of carbon they are used in the EDLC. They've got enormous pores. They have got pores within pores. So you've got a mesopore, inside that you've got maybe hundreds of nanopores, inside that you have millions of hundreds of micropores, and inside each micropore you have thousands of nanopores. So in this way, and the point is there has to be a particular size distribution of these pores, because the electrolyte should be able to flow in the way it has been shown over here. So once again, I'll just explain all these things. There's a current corrector, but this whole stuff is actually electrode. Okay, there's electrolyte inside, but this whole part is these are electrodes, and electrolyte kind of permeates through that. Like if you put a glass of water, you put a lot of rocks in it, and you pour water. The water is finds its place within rocks, and then you are going to have the capacitance. So the A represents all the surface area of all the pores taken together. A represents the electrode specific surface area available, and then D represents the effective thickness, the Debye length. So the thickness, since now you've got electrolytes and electrodes in close proximity, you are going to have to look at what is the effective distance between them. So that is given by the D. So the capacitance for an EDLC is a combination of the Stern layer capacitance, CH, and the diffusive region capacitance, CDIF. So, and as you could see, they were like one after the other. So clearly they are connected in series, and series means you will have to take a 1 by CH plus 1 by CDIF to find the effective capacitance. So now, as I mentioned earlier, the EDLC behavior is very much contingent on porosity. If you have a well-defined pore size distribution, micropores with mesopores, between 2 nanometer, 2 to 50 nanometer max, that really increases capacitance. So I'm talking about the slowest diameter of the pore should be 2 nanometers. In this respect, manipulating porosity is important to enhancing the ionic conductivity of the electrolytes. And from literature, inconsistent capacitance is reported in carbon-based electrodes with pore sizes smaller than 1 nanometer. Yeah, so because the ionic fluid, the size of the ions itself, once it comes close to, couple of, ions will have maybe H2, two atoms of hydrogen, and then H2 plus. H2 is very small, of course, but SO4, if you take, there are 4 molecules of oxygen. So it goes a little bit higher than Armstrong, right? And then we talked about the solvation thing, where you've got the ion at the center, but you also have the solution which is connected to it in such a deep way. So in that bigger solvated molecule usually cannot penetrate pore sizes which are smaller than 1 nanometer. So even though you do a BET, a kind of surface test, and find out, oh, this is the surface area, but then less than 1 nanometer pores will not count towards capacitance. And it has also been found that no linear relationship can be established between the specific surface area and capacitance when using activated carbons and aqueous or organic electrolytes. So there are, so this actually activated carbon and aqueous or organic electrolytes are one of the main building blocks of EDLC, okay? Main building blocks of supercapacitors. But if you see, when you're having aqueous means thin, runny, moving electrolyte, watery electrolyte. And organic electrolytes are also a little thicker, a little more viscous. It's not a linear relationship, capacitance. So the electrolyte that you use also matters. How easily that electrolyte first of all separates the salts and then inserts into those pores. Is there any capillary action in which it gets pulled in? How does it move? How easily, or the viscosity of the electrolyte? There are a number of parameters which need to be studied to actually create a good energy storage device. And as mentioned at the end, pores smaller than 0.5 nanometers are generally not accessible to hydrated ions, 1 nanometer. So wanted to give a little bit idea about the electrolytes, because usually if you read a paper on supercapacitor, the emphasis always is what process or technique can I do to increase the number of mesopores or micropores or nanopores in the electrodes. The electrolytes are somewhat sometimes a little bit more overlooked. So I wanted to give some idea on that. The conductivity of aqueous electrolytes is generally high as compared to the non-aqueous and solid electrolytes because of low viscosity. Because conductivity is related to ionic mobility, right? This is something when if you derive an electromagnetic class, if you or even in batteries class, if you're talking about the conductivity, we know that conductivity is related to the mobility. And then the charge carriers, charge and magnitude of the mobile charges. So if you look at the mobility, if it's an aqueous solution moves very easily. It's a thin, light, water-like solution. So it moves easily, and because of that mobility, the conductivity is improved. Whereas if you're looking at non-aqueous electrolytes, sometimes the organic electrolytes are a little thick and viscous. So because of that, all other things being the same, the conductivity can reduce. And then solid electrolytes, obviously. So the variables in the above equation depend on the solvation effect, migration of the solvated ion, and lattice energy of the salt as well. So the conductivity can be different for different salts in the same solvent due to interaction between anion and cation and volume difference of various anions. So for us electrical engineers, it's easy to understand by the Coulomb's law. This is the Coulomb's law for vacuum. This is the Coulomb's law for some other medium, right? So you can see that epsilon r is all that has come in, is the variation between vacuum and the medium. So if you actually look at it, what happens if epsilon r is say 10 or 100? Uh, the amount of force between Q1 and Q2 is going to go down, right? Which means if the force of attraction, suppose Q1 and Q2 were attracted to each other, uh, if they were in a medium where epsilon r is 100, then it'll be 100 times easier to separate them because the force between them has reduced by 100 times. I hope this is, if this is clear. So then what happens if you are taking some kind of a salt and you put it in, in whatever medium they have, some aqueous medium or non-aqueous, whatever medium. Now, if the epsilon of that medium is high, then it's easy to separate the anion and cation, much easier actually, isn't it? Because the anion and cation, say for example, NaCl, there's Na plus and Cl minus. So to separate them in water is a lot easier than to separate them in air. That's why it dissolves in water easily, because water has epsilon r value of 80. So 80 times easier. So that's what is meant by when I read out this, that conductivity can be different for different salts in the same solvent due to the interaction between anion and cation and the volume difference of various anions and the viscosity. All of these things matter. I'll just, so usually what happens is you might have those materials which have high dielectric constant are very viscous, and the materials which are aqueous probably do not have as high a dielectric constant. Now I said water has 80. 80 is pretty low. I mean, if I want dielectric constants of like 10,000 or 1,000 at least, then comparatively water has very low dielectric constant, right? So the research in this field is often about mixing two, one which will increase the overall dielectric constant of the electrolyte, and the other material which will increase the mobility of the electrolyte. As we saw, mobility enhances conductivity, and so the mixing of the two kind of gives us the best of both worlds. How much, what ratio, that's a matter of research. So that's where I'd say the future work in EDLC, there's a lot of work on carbon, different forms of carbon, carbon foam, carbon aerogel, carbide derived carbon, graphene, carbon nanotubes, activated carbon. There is all these different types of materials, and I put activated carbon at the end because that's really supposed to be one of the best and the most, what to say, it gives a lot of surface area for the reactions to happen. So EDLC electrolytes, as I mentioned, are still an area of active research, and the use of cyclic voltammetry and other tests to measure stability is an important topic. So how do you actually finally decide whether this thing that you've constructed in the lab is really going to be marketable? So you've got to look at stability, you've got to look at charge discharge processes, what's going on. You have to figure that out. So there are methods to do that. And also, since we are talking about nanotechnology here, uh, it's how do I say this? You know, in the nano domain, everything becomes funny. If you've got this ion, and if you've got a big chunk of material mixed in another big chunk of material, it's like mixing two materials. But if you've got a big material, some thick material in which you're dispersing nanofillers, then the way the interface that forms between that nano material and that other bigger material, that interface has its own properties. It generates some special properties, and those need to be studied. Those are still not well understood today. As you saw that, supercapacitor research only started in the 2000s. I mean, 2010 and 2020, only 20 years old. So those modeling becomes a big matter of research. And the reason it becomes such a big matter of research is, if you actually look at it, uh, nano and your device is at the size of maybe at least some few millimeters or few centimeters your device is going to be, or if you're going to take a bigger device. But even if you're going to try per centimeter, you're trying to find out your reactions, these interfaces are happening at the nano level. So the computing power that you need to run, you think that some model will validate the computing power that you need to measure this potential and everything at the nano level. If any of you have been doing say electromagnetic computing of modeling and all that, it requires enormous computer capacity. You would need a supercomputer or some such device. So and computers are very accessible. Supercomputers are not so much accessible. So that's one of the reasons why not many people take up modeling of supercapacitors in its in its full form. So that's a in demand topic as of now. So now I think I've got a lot of material, but I'll try to compress it a little bit now, maybe because I think I have half an hour more, or maybe half an hour, 45 minutes more. And I don't know how interesting this field is being for people, because most of us are electronics engineers. So pseudocapacitors are the other types. Now we looked at EDLC, and what we saw was the surface matters, the electrolyte matters, but pseudocapacitors exhibit much higher capacitance as they instigate certain redox reactions to occur near the electrode surface. So the energy density of SCs pseudocapacitors is decided by two factors, electrode capacitance and cell voltage, right? So the pseudocapacitor mechanism is based on Faraday charge process. What do I mean by Faraday charge process? It is an electron transfer across the electrode interface by oxidation or reduction of a chemical species. So here the electron, not only is the electrolyte or the charge going and sitting, there is some electron, it is some ejecting some electrons into the electrode. Okay, so not into the electrode. The electrode is ejecting some electrons into the chemical species of whatever electrolyte that is. So that is one more excess charge which is coming up. So that because of some reactions with the electrode. So this reaction can be obviously reversible or irreversible. But the good news is, in the reversible process, no new chemical species are produced. And so as we talked about, it's not the same as battery. In the battery, the electrolyte gets consumed, and that's why the charge cycles are maximum of around 1,000 cycles or whatever. But here, that's not the case. Because no new species are produced, you can continue to do this for that many, much larger, maybe 100,000, 200,000 cycles, or even more. So, but now this process of some chemical reaction coming in has a trade-off. This pseudocapacitance can store more charge, but the power performance of this is lower than that of EDLC, because this reaction has to take place. and that reaction takes some time. There's this shrinking and swelling during charging and discharging that happens, and that can also lead to lower cycle life. As I said, when you talk about EDLC, that 500,000 number is correct. For pseudocapacitances, I don't know the exact number, but it is definitely lower than EDLC. Cycle life is a little poorer. So I'll just very shortly describe this. In the development of ultracapacitors using PC, three types of electrochemical processes are involved. One is surface adsorption of electrolyte ions, redox reactions involving the electrolyte ions, and then there is another method called doping and de-doping of CP materials in the electrode. The first two processes rely mainly on surface mechanism, what I was describing right now. You adsorb, then some reaction happens, and then the reactions gets reversed, and in that process, some electrical energy is created and some electrons are created, so that gets added to the number of amount of charge that is stored. The last process, using CP materials in the electrode, relies on a bulk process. So surface area does not matter that much. Okay, the doping and de-doping of materials basically. Okay, the electrode is doped with certain material and the electrode volume itself has that material. So in these cases, but in all these cases, the electrode materials must exhibit maximum electronic conductivity for the distribution of conduction of the electrical current. So just a little bit about the work on pseudocapacitors. When you heard that, what are these electrodes? There are many oxides from the transition metal family which are used: NiO, manganese dioxide, cobalt oxides, ruthenium oxide. Ruthenium oxide is like very much used because it has a huge specific capacitance of 905 farad per gram. But ruthenium, have you ever heard also of ruthenium in chemistry lab? No, because it's like a really rare metal. So even though it's got such good performance metrics, often it is not really used. I mean, because of the money, it's got a very restricted use. So in further works on pseudocapacitors, as you said, these oxides have been studied as electrode materials because these oxides have mesoporous structures. But then you can actually create these oxides in different ways. So for example, if you do a spark plasma sintering of oxides, you're going to get really thick and dense material with very less mesopores. But if you use some other method to create that oxide, you might have better mesopores. Then how do you bind them into an electrode structure? You need to have some kind of a binder. So that binder will affect, that binder itself will go and close up some of the mesopores. So there's enormous number of research which is going on as to how to increase the surface area. All these iron oxide, vanadium pentoxide, which is actually a very good catalyst as well, indium oxide, tin oxide, manganese oxide, all of them are being investigated as of now. And now we come to the hybrid supercapacitors. So one hybridization is, okay, I want some redox reactions, but then I also want some a better, say, charge discharge. So what I do is I take one electrode of EDLC, another electrode of, our pseudocapacitor, and I kind of use them both. So I can store more energy, I can store more charges due to the pseudocapacitor, but then the charge discharge, when the discharging part, as long as it's limited to the other EDLC structure, I'm able to discharge it faster also. So this is one type, hybrid supercapacitor. And the other hybrid, what is generally known as an hybrid supercapacitor, is when the battery type electrodes, when you hear of electric vehicles, they say there's a capacitor and a battery type electrode, which kind of goes in, and you use that a combined supercap battery in your electric vehicles. So going to further work in hybrid capacitors, once again, lithium-ion batteries have the highest energy density of all batteries. I'm sure may not have the highest energy density, but they are the workhorses, right? If you actually look at all the EVs, they're using lithium-ion. And it's got some limited cycle lifetime, 100 to 500 cycles, definitely better than some of the other lead acid batteries and all that. Additionally, the charging rate is also a problem with lithium ion batteries. We have discussed this already, that supercapacitors have a battery like, they charge much faster, discharge much faster. So this led to the development of battery like hybrid capacitors. So for this development, 4 things are required. It requires a suitable electrode material which must have a large surface area while assisting the mobility of electrons and ions. So what you're doing is you're taking that battery, you've got 2 electrodes, you've got an anode and a cathode, and one you're replacing by a supercapacitor like electrode. Yeah. So to do that, you've got to look at 4 things. You've got to look at improving the conductivity of the electrodes. Then you can use nano architectures for electrodes to minimize the diffusional pathways. So nano architectures, we'll talk about this. I don't know whether you've heard of this, 3D printing and all that. There are many ways to actually do that, developing 3D materials and create the kind of architecture, the kind of surface area that we want. And then that's the third thing, developing those 3D materials to accelerate ionic diffusion in several directions. So to increase that diffusion, and then minimizing the diffusional activation energy of the ionic species. So activation energy, so the diffusion should happen easily. We talked about this activation energy, this dissolving of that salts, which actually create that activation, create the ions. So that we want to reduce. So here is kind of a small idea of all the different types that we discussed. This composite electrodes, asymmetric pseudo. With EDLC, you have one kind of supercapacitor, this composite. This composite is basically like you could have a composite fluid. As we talked about, mixing different kinds of electrolytes, you could have a composite electrode itself, mixing carbon with, for example, I don't know whether I've talked about it later, but you can coat the carbon with certain materials which will give a good dielectric constant, much better dielectric constant. So that's possible. That could be one composite. And then the rechargeable battery type we discussed. So all these things are possible. Conducting polymers are also possible in pseudocapacitors, just like metal oxides. We had that. I think I skipped over it. So these are all materials which can be used to create a good supercapacitor. So now coming to the latest trends in supercapacitor technology. This is going to be a little different from the way we use this. Miniaturized energy autonomous systems basically means that autonomous means self-contained creating of energy. So I'm not visible on camera, but I'm moving my hands and I have maybe a small device on my hand, which is using that hand movement to create energy. So I think many of us students, they do these kind of projects, walking and then generating energy out of walking, generating energy out of movement of car, all of that, right? So that's what this miniaturized energy autonomous systems mean. And obviously you need to, if you are generating that energy, you need to immediately have some very small, tiny storage device which will store it as well and not discharge it easily. So there supercapacitor comes into picture. And then once it is stored, then you can use wireless transceivers, signal sensing, all of that, and transfer the energy and all that stuff. So this MEAS, the miniaturized energy autonomous systems, are now coming into play because we've most of us know about the renewables. Renewables will slowly become completed technologies and will be less funded. But then people are focusing, we are even more greedy for energy. We're looking at all the kind raw energy. So these will also become, I think, in the future, from what I'd read, if you look at all the top Ivy League colleges, like even Georgia Tech, uh, MIT, they are focusing quite a bit of effort on these miniaturized, energy storage systems. So, so these sources, what are these sources? They comprise of, they could be solar, they could be vibrational, they could be thermal. You could probably extract some energy out of radio frequencies. So many frequencies are, go unused. Use, for example, you're putting a TV on a particular channel, but all the other frequencies, what do you do? Why don't you make use of them? And then, of course, the human body, blood flow, body heat for electrical power consumption. So this is here absolutely superconductors shine. So for use in this MEAS, you got to have a particular way these supercapacitors are made. And the main thing is mechanical deformation. If you're wearing something, it should twist around your fingers, or it should be able to, if you're wearing it as a dress, it should be able to stretch and bend and fold, while reducing their area to fit into very, very small compact devices. So how does that get made? We'll just have a look at that and we will end this. So I'd like to talk a little bit about this 3D architecture for supercapacitors. So I'll just show you the picture first. You can see this is how a 3D architecture is built. And that looks pretty big, but actually 3D, you can go on and make 3D architecture. You can build something atom by atom. That's the limit. So it's a very, very interesting, 3D printing is a very, very interesting topic. So why would we need this for supercapacitors? Because we need a lot of surface area. We need a lot of electrochemically available active sites on the electrode surface. But not all of the electrode surfaces in supercapacitors is available. Only the places where active materials and electrolytes contact each other. So to enhance that process, to enhance that flow, the electrode capacity for SCs, 3D architectures for electrodes have been devised nowadays, which can provide much more number of active sites. So you're basically trying to create that nanopores, mesopores by hand through this 3D printing according to the way you want, and also create a sense of flow, make it easier for the electrolyte to flow through them. That's the idea of using 3D architectures for supercapacitors, right? These electrodes can help support effective contact between active materials and electrolytes, easy electron transportation between current collector and active materials, and effective accessibility on the current collector to enhance electrochemical activity. For example, NiOH-based electrode has been used widely in supercapacitors because of its flexibility in forming 3D structures. It can be coated atop carbon electrode. This is what I was talking about. Yes, as I said, uh, it can be, coated atop carbon electrode with larger surface area to give rise to hybrid electrodes with higher conductivity and higher dielectric strength. No, I think it's dielectric constant. I'm sorry about this, but I'll check and I'll let you know. So this sort of thing, double hybrid kind of structures is possible by dropping it from atom to atom. 3D structures are possible, and you can have a look here. This is the 3D printing anode. First, the anode is printed, then the cathode is printed, which is in green color, and then the inside you are filling it up with electrolyte such that the electrolyte can, there's beautiful space for electrolyte to flow and see a lot of it. Just imagine if this same structure was just, completely closed, then electrolyte will only flow at the top. But now it is able to see the whole anode, cathode, anode, cathode, anode, cathode totally, and then you are able to get a much better, what to say, much better performance. So here you can see first the anode was 3D printed, then the cathode, and then it was filled with the electrolyte. And if you actually look at it in SEM, this is how it looks. At 150 micrometers, at 50 micrometers, you've got zooming in of at different lengths. And so this is one of the papers. The DOI of the paper is given. If you can refer to these papers if you are interested. Similarly, I'll just talk about two more different types of supercapacitors and in this. There is also something called the paper type supercapacitors. So you really, this is really interesting because it's really flexible. You can, you can fold it and you can insert it anywhere you want. So it can be very easily manipulated into other modified structures. Yeah. And these capacitors can also be used in wearable health monitors, electronic textiles, and electronic skins. So what do you mean by electronic skin? So, Elon Musk got a little bit trolled for saying that, we'll have a chip in our brain to reduce or monitor Alzheimer's and all that. And people started laughing about him that, you are robotic, you must be having some kind of chip in your brain. So, but this technology is real, you could actually pretty much stitch an electronic device to your skin where it can monitor your health, it can monitor your blood pressure, it can monitor so many things. And if you, before you say this is so, this feels so wrong, you should remember that, if you look, a lot of our grandparents and all that have lived longer lives because of a device within their hearts called pacemaker, right? So my grandfather had a pacemaker, so I know that, that helped him live a longer and more productive life. So it could be, after testing and after proper due research, it's possible that you would have this sort of supercapacitors which power a small electronic device right in your skin. And you could also have it little less intrusive, would be putting it on a textile, on a band, something like that, right? So customized supercapacitor architectures, pyramid structures, honeycomb-like structures, living hinge structures, they can provide these structures by customizing the supercapacitor structure. You will be able to tune, you can stretch those capacitors in any direction. For example, one supercapacitor with a honeycomb-like structure, it's got a specific capacitance of 227 millifarad per cm square. That's quite a bit. We usually have microfarads in our lab, right? This is 227 millifarads, almost close to a farad per centimeter square. And it is stretchable up to 500% without changing that capacitance. That's so cool, right? You can pull around capacitor. We could pull around our capacitance in the lab and stretch it 500 times. That's amazing. Not 500 times, sorry, 500%. That's 5 times. So this structure was reported to maintain 98% of its capacitance over 104 cycles. So now we've come down for paper type capacitors and these sort of applications. We do not have that kind of cycle life yet. No 500,000 cycles. It's just 104 cycles or so. So there are always pros and cons to everything. Similarly, Wang et al. Had developed flexible manganese oxide nanosheets. and reduce graphene oxide. It mixed two different types of nanosheets into a paper like composite using a simple ultrasonication, filtration, and hydrolysis method. Ultrasonication is one good method to disperse two materials together and two nanomaterials together, because it breaks down. See, nanomaterials, they don't like to remain nanomaterials because that surface area is very high. They tend to bond together. They tend to, stick together more. Because the effective active surface energy is higher. So that tends to cause them to agglomerate, and ultrasonication can actually help break it down and separate it. So that's one method. The integration of RGO-NSS into MnO3. NSS basically means nanostructure. Into this manganese oxide provides a large surface area, because basically the graphene oxide, as I said, all these carbon nanotube materials have a very large area. And uh, this actually showed specific capacitance of 409 farad per gram inverse. That's unbelievable. The earlier one was 227 millifarad. This is 401 farad per gram. Okay, so the gram, we cannot compare them because that was cm square and this is per gram. And but that seems pretty big. And then high cycling stability at 3000 discharge cycles. So there's so much work which is going on. We could continue to go on and on all these materials. These are some pictures. You can see this is would be one of those paper supercapacitors, which are fabricated with PANI. PANI is one material which is being tested for supercapacitors. So I'm not aware of too much about this, but it's a very exciting field if anybody wants to go into it. And then finally we'll come to clothing, which has got supercapacitors in it. The future of electronic devices is expected to include wearable electronics with stretchable circuitries, implantable sensors, and smart skins. Again, I've repeated myself, I guess. But here you could have flexible fiber-like supercapacitors. Yeah, and ultra-thin fiber, which can actually still maintain a very good electrochemical performance. So with respect to a device configuration of fiber-like electrochemical capacitors, there are two types available. There's a coaxial fiber-like supercapacitor and two-ply fiber-like supercapacitor. So you can, I don't have the picture of the coaxial, but coaxial we know. We talk about coaxial cylinders and all that in electromagnetism. It's exactly like that. You've got a material electrode inside and something outside, which together creates a supercapacitor-like system. And two-ply fiber-like is more like a double helix structure of a DNA. Two things, two say threads are intertwined. So the former is this one, the coaxial fiber-like structure supercapacitors is fabricated by assembling capacitor components like this core fiber electrode. There's this gel polymer electrolyte, and then outer there is one more coated electrode layer by layer. It's exactly like our power system cable with an electrode inside. There's some material in between, and there's an electrode enclosing it outside. That's how the coaxial fiber-like supercapacitors look. But the material inside, it's not capacitive material. It's not a dielectric. It's a electrolyte. And the latter has been invented by twining two fiber-like electrodes together with a separator or gel polymer electrolyte. We have a picture of that. So you've got this polymer electrolyte, and then you have this material, and then you have some 3D structure. So this is kind of a picture of actually in if you zoom in, if you hold it, how this whole capacitor will look. And you can see that that supercapacitor can be stitched into a normal material. I hope this is visible. And then you connect it to a a conductor, and that can be used to actually store some energy. So these are, lastly, I'll just talk maybe for 2 minutes about the challenges and solutions. Main challenge, one is energy storage, and the other is the cost of supercapacitors. So if you're looking at the traditional supercapacitors, which mainly use carbon, right now what people are finding is, suppose maybe even in your colleges, and I know this is there in VIT, huge amount of waste product is created. And what do you do with that waste product? You burn it in an incinerator. In the process of burning, you also sort of I'm sure in that process of burning, you would probably get a lot of charcoal. You will also burn and use that energy, utilize that energy, store it in some other maybe supercapacitor or battery system. And then what do you do with that charcoal? That charcoal can be converted into activated carbon. And that is really helpful because according to one of the researchers' investigations, Mr. Andrew Burke, in carbon-carbon SCs, the carbon is responsible for about 60% of the total material cost. And the total electrode material cost is 0.1 centimeter, 0.1 cent, sorry, 0.1 cents per farad. See, I'm an Indian, I don't understand American money that well. So, whereas when you are burning biogas and then you're creating that electrode material, that costs only around 0.001 cent. Somebody can probably convert it to paisa and let us know how much that costs. So that's really helpful, right? If you actually are able to derive uh, carbon from burning biomass and use that for your electrode. So that's one solution, that it's an order of 2 magnitudes, divided by 100. Your cost becomes divided by 100. So this has a huge potential, and then people are now going left, right, center. Okay, carbon derived from rice husk, carbon derived from this, carbon derived from that, and this is the surface area. We are able to equivalently show a good amount of capacitance in supercapacitors. So this is one area of research. And but to activate that carbon, again, you would have to use chemical agents such as potassium hydroxide, sodium hydroxide, salt, all this stuff which has to be used to create activated carbon. Those are expensive still. So that will add to the expense and they will also affect the final properties of the electrode. So that is the limitation right now of using biomass waste. And we hope that researchers will find lower cost replacements, because here again it becomes like a battery-like thing, right? All these things are used in battery and then they get consumed as you create activated carbon. Yeah. So yes, so I think I'm kind of on time. Thank you. And the stage is open for questions, if any. And I just want to say that I am myself kind of, I'm an electrical engineer, as are all of you. So, but I was interested in making some of these materials for my use. So I started dabbling into this. So if I do not know the answer to some question that you have, I would just honestly tell you that I'll get back to you on that. So from whatever we have presented, if you have any questions, anyone, please feel free to ask.
Thank you, ma'am, for sharing your valuable thoughts on supercapacitor versus batteries, types of supercapacitors, and also you have given the great idea for upcoming researchers to have their research work on modeling of ELDC, EDLC, and also you have discussed the further work on pseudocapacitors. I think this will be very useful those who are doing research now. So thank you, ma'am. Now it's time for the participants. If you are having any doubts, you can get it clarified. Unmute your mics and ask your queries. Any doubts from the participants? Thank you, ma'am.
Okay, thank you so much. So there's one part I just wanted to mention that I've not covered is how do you characterize once you make the supercapacitors, how do you characterize it? So I thought there might be some questions on that, but yeah, so that maybe if I share, do I have to share the PPT or something?
Yes, ma'am, you can share the PPT if anyone asks.
If anyone asks, you let me know. If you really have, if you want to characterize, okay, this is good or this is bad supercapacitor I have created, there are some just 3 methods which are used and you can get to know about them. Thank you so much. Thank you for calling me. Thank you to Vardhaman College of Engineering. Thank you to Monica ma'am for taking this effort and putting together this FTP pretty much single-handedly. I've been interacting only with her and wish all of you the best of luck. Thank you.
Thank you, ma'am. Thank you. Thank you for your time. Thank you all for
Okay.
the participations. The feedback link has been shared in the chat box. I request all the participants to fill it. And I request all the participants to join back for this afternoon session at sharp 1:30 p.m. Thank you. Thank you all.